Let us summarise what we've learned so far in the calculus of variations. We started off by defining the simplest functional, and it's of this form here: I is equal to the integral from a to b over function f of x, y derivative by dx. And we've said that if the Euler-Lagrange equation here, partial f by partial y minus d by dx partial f by partial y derivative is equal to 0, then this value of I is stationary. But we don't know whether it's a maximum or a minimum. We only know that it is stationary. Now, we looked at simplifications in the first course, so if there was no explicit dependence on x within this functional, then we could rewrite the Euler-Lagrange equation in this format here: f minus y derivative partial f by partial y equals 0. And we've seen in the first course that that helped us to simplify a lot of the mathematics. Also, if there's no explicit dependence on x or y within this equation, then we could write it as partial f by partial y is equal to a constant. In the second course, we've tried to answer the question whether the extremum is a maximum or a minimum. One of the ways we've seen that we could do this is the Legendre test for weak extremum. So we said that if an extremum exists, that is, the Euler-Lagrange equation is satisfied, and the range of integration is small, and the sign of this part of the derivative, partial squared f by partial y derivative squared, doesn't change sign on the interval ab, then we can say that the extremum I is a maximum for partial squared f by partial y derivative squared less than 0, and it is a minimum for partial squared f by partial y derivative squared greater than 0. We also seen that if we try to work out a characteristic equation for our problem that we're working on, and if this goes to 0, then it turns out that the value of our extremum is evaluated as a function of the endpoints only, that is, the boundary conditions. We also went ahead and derived the Jacobi accessory equation, and we derived it using two different methods, and this is the accessory equation here. And if you like, this is an example of a second order version of the Euler-Lagrange equation. We then looked at the idea of conjugate points. So if this function here, u of x, is a solution to the Jacobi accessory equation, and u of x is equal to 0 at some point a, then it's going to be equal to 0 at all points conjugate to a. We then looked at the Jacobi test for weak extremum, and this is similar to the Legendre test, but we add on one proviso, and that is that the conjugate point a' doesn't lie within the interval ab, it must lie out with it. Given that that's the case, then the rest of the Legendre test conditions apply, and we can say that I is a maximum for partial squared f by partial y derivative squared less than 0, and it's a minimum for partial squared f by partial y derivative squared greater than 0. We then looked at an analytic method of finding the x coordinates of the conjugate points. If u1 of x and u2 of x are independent solutions of the Jacobi accessory equations, then the x coordinates of the conjugate points are given by u1 of x divided by u2 of x is equal to u1 of a upon u2 of a, such that we can write partial y by partial c1 divided by partial y by partial c2 is equal to partial y by partial c1 divided by partial y by partial c2 at point x equals a. We also seen that if we have an extremum through a point A and it has an envelope E, then the points of contact of the extremal and the envelope E are conjugate to point A. That's all for this video. Let's continue on our journey through the calculus of variations.